Algebras. Welcome to your Chapter 7 Lesson 2 notes. We are going to talk about factoring the difference of two perfect squares today. So, we need to recall what each of these words means because in math, we are not very creative when we name things. We either name things after the first person that did it or the first person who figured it out, or we name things after exactly what is happening. This is a case of we have named this after exactly what is happening. Okay? Difference is subtraction as a math word. Two is how many things we have. Two. Perfect squares is what those things are. Perfect squares, of course, are things that are the results, are the product of a number times itself, right? So when you take their square roots, they come out as an integer, or in this case, possibly a variable. Okay, so the difference of two perfect squares is when you have one perfect square minus another perfect square. In our case, polynomial wise. So they're unlike terms where we have the subtraction going on between them. These factor in a very specific way. But the first thing I want to go over is what it looks like to have dots or difference of two perfect squares and what it looks like when you don't have difference of two perfect squares. Okay? This is dots. X squared is a perfect square. 16 is a perfect square. We are subtracting them. So this is perfect square minus perfect square. That is the reason that this is difference of two perfect squares, or dots. Okay? 4x squared is a perfect square. 4 is a perfect square, and x squared is a perfect square. So the whole term is a perfect square term. 81y squared is a perfect square because 81 is a perfect square and y squared is a perfect square. The whole term is a perfect square, and I'm subtracting those two terms. This is, again, dots. Perfect square minus perfect square. Okay? These are factorable. These are not, because these are not dots. Okay? No dots over here. What's wrong with this one? Because I've got a perfect square and a perfect square. What's the matter? Why is this not dots? What's going on between them? Addition. This isn't the difference of two perfect squares. It's the sum of two perfect squares. That's not a factoring thing. Okay? If it's not subtracting between them, it's not dots. It won't factor the way these will. 16y squared is a perfect square. X squared is a perfect square. There's subtraction happening. What's the matter? Three is not a perfect square. That's it. It's not, so it can't happen. This is not factorable by dots or in general, but that's all right. Difference of two perfect squares, if you have it, two terms that are both perfect squares that are not like terms that are being subtracted, if you have that, it always factors the same way. I mentioned it in chapter 6 when we were looking at special case binomial multiplication. This is a special case binomial multiplication backwards. This is what happens. It always goes back to take the square root of the front term, put it in the fronts. Take the square root of the back term, put it in the backs, different signs between them. Because you have these conjugates here, which is a vocab term I used in chapter 6, their middles cancel out. Okay? Because they're opposite signs here. So, if I am asked to factor the difference of two perfect squares, or if I am asked to factor a polynomial that is the difference of two perfect squares, because I have to now recognize it. If it's given, I have to recognize this is a perfect square minus a perfect square. Here's how I do it. I always have my equal sign, set up two empty sets of binomials, empty sets of parentheses, ready for binomials. Take the square root of x squared, x. Put an x in each front binomials because this was the front term here. Take the square root of 16, 4. Put a 4 in the back of each of the binomials because this was the back term of dots. Then to finish it off, one of these binomials gets a plus sign, the other gets a minus sign. You're done. Now I want you to look at something. In my example, the answer to this exact same problem was x minus 4 times x plus 4. And what I just wrote was x plus 4 times x minus 4. Why are these answers exactly the same? Because multiplication is commutative. So it doesn't matter which of the two binomials came first and which comes second, as long as those are the exact two binomials that are present. Okay, stop there, take that in, and then we're going to do a whole bunch of examples. Ready? Okay. So here's two more examples showing you how to do it. I am now going to just do all sorts of binomial examples down here. Okay? So x squared minus 100. Yep, there's dots. Both perfect squares, so I start with my two empty sets of binomials. My equal sign, of course. What's the square root of x squared? X's go in the fronts. What's the square root of 100? 10. 10 goes in the backs. Different signs between them. Done. Next, g squared minus 81. Yep, there's dots. Perfect square minus perfect square. Okay, two empty sets of parentheses. Square root of g squared is g. That's in the front, so that result goes in the fronts of my two binomials. Square root of 81 is 9. 9 goes in the backs of the two binomials. Different signs between them. Okay, p squared minus 36. Yep, dots again. Perfect square minus perfect square. What's the square root of p squared? P goes in the fronts. What's the square root of 36? 6 in the backs. Different signs between them. As long as you've got a p minus 6 and a p plus 6 being multiplied together, you've got the right answer. Okay? As long as one of those is 1. One of those is each. Okay, next. Dots. Yep. Yet again. What's the square root of 49? 7. What's the square root of r squared? R. So 7r goes in the fronts of both binomials. What's the square root of 25? 5. What's the square root of s squared? S. 5s in the backs of both. Different signs between them. M squared minus n squared, both perfect squares, subtracting empty sets of binomials. Make sure you're doing this right along with me, making those empty set of binomials first, taking that square root, putting it in the fronts, taking that square root, putting it in the backs, different signs between them. Every time you've got to make sure you notice, you recognize, and you do that each and every time. You must practice this. D to the fourth is a perfect square. 4 is a perfect square. You're subtracting them, it's dots. So, d squared minus 2, d squared plus 2. There we go. Done. This is it. Every time, as long as you've got dots, this is how it factors. Okay, here, 49 is a perfect square, minus v squared is a perfect square. Difference of two perfect squares, two empty sets of binomials. Take the square root of the front term, put that square root in the fronts. Square root of 49 is 7. Take the square root of the back term, put it in the backs. Square root of v squared is v. Different signs between them. Try those last two right now. Pause it. Try those last two. Let's see how you do. All right, how'd you do? Check 8 and 9. Check them all. Make sure you've done this with me. Maybe even take out a blank sheet of paper and do it again right with the video, because you've got to practice this. Okay, you've got to practice this operation. Speaking of things you should practice, At the beginning of the year, I told you you had to memorize your perfect squares. I also told you that any variable that has an even exponent is considered a perfect square. It would be a great idea to make sure you have a list of perfect squares that you have memorized so you can identify them right away. Okay, so we're going to list some perfect squares right now. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'm going to keep going because why not? 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. There are the first 20 perfect squares. Those you should be able to memorize and identify. It's only 20 out of 400 numbers. So what does that tell you? Perfect squares are rare. They do not happen that often. If out of the first 400 integers you only end up with 20 perfect squares, they are extremely rare. What else are perfect squares? Any variable raised to an even exponent. So x squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th, x to the 12th, x to the 14th, x to the 16th, x to the 18th, x to the 20th. I could keep going there, obviously, into infinity, but anytime you've got an even exponent, that is a perfect square. So those are perfect squares. And that's the same for y squared and y to the 4th and y to the 6th and y to the 8th. Okay? Any of those variables that have that even exponent, they are a perfect square. Make sure you write those down. Okay? Make sure you know those. Make sure you're working on memorizing those. You've got to be able to identify your perfect squares so that you can identify dots very easily. Okay? Guys, use the examples. Write out your perfect squares so that you work on memorizing them. Make sure that when you see two binomials being subtracted, right? Or excuse me, make sure that when you see two terms being subtracted, check them for perfect square minus perfect square so that you know how to factor them every single time. Make sure you know what I mean by this. What's dots, what's not. All right. This has been Chapter 7, Lesson 2 notes. Please make sure you take the notes with me. Please make sure you try the homework practice problems right now. Not now, right now. Go ahead. I'll be seeing you guys.